So when you look down at the fuel gauge on your dashboard, you are basically being lied to. I mean, maybe not maliciously lied to, but you aren't actually looking at your fuel.
Right, yeah. You're looking at an illusion.
Exactly. You are looking at this carefully calibrated illusion. It's really just a tiny mechanical translation of electrical resistance.
And it is a completely necessary illusion. Because, whether you're miles offshore in a center console taking on heavy swells,
oh yeah,
or you're just driving down this desolate stretch of highway at 2 a.m. where the next gas station is literally just a rumor.
It's a terrifying feeling.
It is. And in that moment, you are putting absolute faith in a tiny dial that has zero direct physical connection to the actual gasoline burning in your engine.
Yeah.
I mean, we all know that universal feeling of low-level panic when that needle hovers near empty.
Oh, absolutely. And it is entirely dependent on an invisible electrical signal. So today, we are tearing apart that illusion. We're doing a deep dive into the engineering of VDO fuel gauges and aftermarket sender troubleshooting. The mission here is to really demystify the translation.
Right, getting down to the nuts and bolts of it.
Because, how does a mechanical movement happening inside a dark, sloshing, completely sealed tank become a highly reliable electronic reading, the kind of reading that keeps you from getting stranded?
That's a great question.
Okay, let's unpack this.
Well, we really need to start down in the tank itself, out of sight. Because before you can even begin to trust the display in the driver's seat, you have to trust the signal source.
Makes sense.
And the entire ecosystem down there basically consists of 4 core components. You have the float mechanism, the variable resistor sensor, the mounting flange that seals it all up, and the voltage control unit.
And the interaction between these parts is, honestly, it's a masterclass in resilient engineering. It starts with a buoyant float resting directly on the surface of the fuel.
Right, and that float is attached to a pivot arm.
Yeah. So as the engine consumes fuel, the liquid level drops, obviously.
Yeah.
And that float physically drops right along with it. But the actual magic happens at the pivot point of that arm, right?
Exactly. So that pivot point sweeps a contact wiper across a resistor board. So what it's doing is translating a spatial reality, the physical depth of the fluid, into an electrical vocabulary.
So it's basically a dimmer switch attached to a mechanical bobber.
Yeah, that's a perfect way to look at it.
Like, imagine the tank is being filled, the water level rises, the bobber floats up, and as it pulls up, it slides the dimmer switch higher.
Turning up the brightness, so to speak.
Right, meaning it increases the electrical resistance in the circuit. And the VDO system uses a very specific mathematical window for this, 10 to 180 ohms.
Yes, 10 to 180 ohms.
So when the tank is completely topped off, you hit what is called ohms full. The sender produces maximum resistance. It sends that 180 ohm signal up the wire to literally push the dashboard needle up to full.
Yeah, that 10 to 180 ohm range is the critical language of the entire system. But, your bobber analogy raises an immediate, massive engineering problem.
Oh, because of the movement.
Exactly. Boats hit choppy waves, trucks take sharp turns, they hit potholes. The fluid in a moving tank is never just sitting perfectly still. It is violently sloshing around constantly.
Right. So if that mechanical float is bouncing up and down over every single wave, it's constantly sliding that dimmer switch back and forth.
From 50 ohms to 120 ohms and back again.
Yeah. So my dashboard needle should look like a metronome. It should be sweeping wildly from empty to full every 2 seconds. Why doesn't it?
Well, what's fascinating here is how the system is intentionally designed to filter out that exact physical noise. It uses integrated dampening.
Okay, dampening. How does that work?
First, you have the mounting flange anchoring the geometry down in the tank. And the voltage control unit ensures the baseline electrical feed remains perfectly constant.
So it's completely ignoring whatever noisy surges the alternator is throwing at the battery.
Exactly. But the real trick, the really clever part, is the dampening built into the gauge itself.
Wait, how does the gauge dampen the signal? Is it like a tiny mechanical shock absorber in the dial?
No, actually. In traditional analog setups, it's often thermal dampening.
Thermal, like heat.
Yeah. The gauge uses a bimetallic strip inside the dial. So as the varying current from the sender flows through a little heating coil wrapped around that strip, the strip heats up.
Wait, the electricity is literally heating up a piece of metal.
Yes. And as it heats up, it physically bends. And that slow bending action is what physically drags the needle across the dial.
Oh, wow. So because it physically takes time for the metal strip to heat up and cool down, it naturally, completely ignores rapid momentary spikes.
Exactly. A single wave sloshing the float might drop the resistance for half a second, but that simply isn't enough time to change the temperature of the metal strip.
That is wild.
Right. By utilizing thermal inertia, the gauge averages out the frantic splashing data. It only registers the true, steady overall decline of the fluid volume.
That is remarkably elegant. Okay, so down in the tank, we have our dampened mechanical bobber. It's translating fluid depth into a steady 10 to 180 ohm electrical signal.
Yes.
But now we have to visualize that invisible current. We hit the display divide. How do we actually want to look at this data?
Right, and we essentially have two competing philosophies here, analog dials and digital screens.
Which represents a classic systems engineering trade-off.
Okay.
Let's look at the analog VDO gauges first.
Sure. So these are your traditional printed dials with a physical needle sweeping across the numbers.
The classics.
Right. They operate on simple direct voltage, utilizing that bimetallic strip we just talked about, or sometimes basic electromagnets. They are really the rugged workhorses of the dashboard.
Yeah, and the absolute beauty of the analog gauge is its lack of complex electronics. I mean, it gives you an immediate continuous reading.
But there is a trade-off.
Always. The trade-off is that they really only offer moderate precision. You don't get a perfect percentage point, and occasionally you might have to manually calibrate them.
Right. And then you have the modern alternative, which is tearing out that old sweeping needle and dropping in a shiny digital VDO gauge.
Which everyone loves to do nowadays.
They do, and these utilize bright LCD or LED readouts. They process that raw analog ohm signal through a microprocessor to give you a highly precise numerical readout.
Down to the decimal.
Exactly. They are brilliantly backlit, and they're often entirely self-calibrating, too.
Okay, but here's where it gets really interesting. Because I have to aggressively push back on this modern assumption that a digital upgrade is inherently better.
I completely agree. Let's hear it.
We are talking about equipment used heavily in marine environments. Saltwater spray. Constant heavy vibration, marine alternators that occasionally just hiccup and throw weird voltage spikes.
Oh, absolutely.
You're telling me I should trust a sensitive microprocessor-driven LCD screen over a rugged 50-year-old analog needle design when I'm 40 miles offshore?
You absolutely shouldn't, unless you are totally certain your electrical environment is pristine. Understanding your specific operating environment is critical systems design.
Right.
The push for shiny digital upgrades often completely ignores how hostile a marine environment is to a microprocessor. I mean, to achieve that high precision, digital displays require a highly stable voltage.
That you rarely get on a boat.
Exactly. If your alternator throws a sudden voltage spike, a digital screen can freeze, it can glitch, or its circuitry can literally fry entirely.
Whereas an analog gauge just kind of shrugs it off.
Precisely. A massive voltage spike might make an analog needle twitch aggressively for a millisecond, but it won't kill the gauge. Plus, analog dials are vastly more robust against moisture intrusion.
That makes sense.
If a seal fails and salt spray gets behind the dash, a traditional analog gauge will often just keep running. A sensitive digital circuit board, it's going to immediately short out and die.
So sometimes fewer electronic components simply mean fewer points of catastrophic failure when you are out there battling the elements.
Exactly. Sometimes simpler is safer.
So the analog gauge might not tell me I have exactly 42.6% of a tank left, but its absolute simplicity is its greatest defense mechanism.
Well said.
But whether you choose the rugged needle or the hyper-precise digital screen, eventually the chain of communication breaks down. At some point, the system is going to start lying to you.
It's inevitable, and that is the exact moment you have to transition from being a vehicle operator to being an electrical diagnostician.
Right, time to break out the toolbox.
Yeah. Diagnosing a malfunctioning VDO system means reading the symptoms on the dash to trace the disease hidden in the wiring. And because we understand the underlying physics of how the circuit works, we can decode exactly what that broken gauge is trying to tell us.
Okay, let's start with the flat line. The display shows completely empty, or it just entirely drops out with meaningless readings.
That is an open circuit.
Right, an open circuit.
Yeah.
But why does a broken wire actually cause the needle to drop to zero?
Because the electrical loop has been physically severed, a wire snapped or maybe a ground connection vibrated loose from the hull.
So the current stops.
Right. Without a complete circuit, zero electrical current flows up to the electromagnet in the dashboard gauge. And inside that gauge, there is a tiny return spring.
Yeah.
And its only job is to constantly pull the needle toward empty. So without any electromagnetic force fighting against that spring, the spring simply wins. the needle drops dead to the peg.
Okay, so an open circuit is a dead signal. Zero current, the spring wins.
Got it.
But what about the opposite problem?
The panic attack.
Yeah, the system has a massive panic attack. The needle violently jumps, flickers rapidly, or just gets pinned at maximum full and absolutely refuses to move.
That is your classic short circuit. Somewhere in the wiring harness, the protective insulation rubbed away, and the hot wire is touching bare metal.
So it's grounding out before the signal ever even reaches the resistor board down in the tank.
Exactly. And electricity always takes the path of least resistance. So it ignores the 10 to 180 ohm sender unit completely. Because the resistance has dropped to near zero, the gauge suddenly gets hit with the maximum unfiltered current straight from the battery.
Oh, wow. Which means that massive surge voltage just overwhelms the tiny electromagnet inside the dial.
Right, and it violently pulls the needle all the way past full.
So a dead needle means a severed loop, and a pinned needle means a bypassed loop.
Exactly.
But what if the needle is just acting like incredibly lazy? Say I just pumped 40 gallons into the tank, but it takes 20 minutes for the gauge to slowly, sluggishly creep up to full. Is the mechanical float just getting physically stuck on some debris in the tank?
Well, a stuck float is definitely a mechanical failure you see out there, but the symptom for that is usually static.
What do you mean?
Like, the needle stays at exactly half full for 3 days straight no matter how much fuel you burn because the arm literally cannot move.
Oh, I see.
But a sluggish, delayed, or wildly inaccurate response like you described, that's usually a completely different disease. It's corroded contacts.
Because we're dealing with salt water and high humidity creeping into the wiring.
Right. Moisture creates oxidation on the metal terminals. Now, remember the math we rely on. The gauge is expecting a clean 10 to 180 ohm reading from the sender.
Right, the dimmer switch.
But corrosion acts as a resistor itself. It physically adds unintended electrical resistance to the circuit.
Oh, I didn't think about that.
Yeah, so the sender might be perfectly positioned at half a tank trying to transmit, say, 90 ohms, but the corroded, rusty terminal adds another 40 ohms of resistance just by being dirty.
So the gauge receives 130 ohms instead.
Exactly. And it does the only thing it can do. It moves the needle higher, completely lying to you because the mathematical translation has been corrupted by the rust.
And then, of course, you have internal resistor failure, right? Where the actual tracks on the sender unit just wear out after years of use.
Yes, exactly. As the float arm drags back and forth across the resistor board thousands and thousands of times over the years, it physically wears down the conductive material.
So you get dead spots.
Right. When the arm hits one of those worn-out patches, the resistance suddenly jumps to infinity, and your gauge either drops out completely or just floats aimlessly.
If isolating a phantom ground wire or a worn-out resistor board while getting battered by sea spray sounds like an absolute nightmare, which it does, the obvious question is, how do we stop this from happening in the first place?
Maintenance.
Right. How do we keep the system honest?
Well, if we connect this to the bigger picture, maintenance is all about fiercely protecting the integrity of that electrical translation. You don't wait for the system to fail on you out on the water. You actively verify it.
And that means stepping in with a multimeter.
Absolutely.
Actually pulling the sender wires and checking the continuity. You are verifying that the sensor is legitimately producing that specific 10 to 180 ohm sweep as you manually move the float arm up and down.
Right. And if your multimeter shows the ohms jumping erratically as you move the float, you know the internal resistor is shot. The sender belongs in the trash.
But what if it tests perfectly?
If the sender tests perfectly on the multimeter but the dashboard gauge is still dead, well, then you know the disease is isolated somewhere in the wiring harness between the tank and the helm.
So you just isolate the variable to find the truth.
Exactly.
And to protect that wiring, you really have to fight off the corrosion before it even starts. Sealing connections, applying protective dielectric coatings.
Yes, keeping the grounding loop absolutely pristine so you don't introduce that phantom resistance into the math.
And crucially, ensuring absolute component compatibility. I mean, this is the #1 cause of headaches with aftermarket upgrades.
Oh, it really is. Someone buys a shiny new digital gauge for the dashboard, but they leave the factory sender unit down in the tank.
Right. And if you mix an aftermarket sender that operates on, say, a 0 to 90 ohm scale with a new VDO gauge expecting a 10 to 180 ohm scale, the mathematical languages are totally incompatible.
The hardware might be working perfectly, but the translation is complete gibberish.
It's like someone speaking French to someone expecting Japanese. The gauge will just output complete nonsense.
Exactly.
But, there is one detail about maintenance in the sources that really caught me off guard.
Oh, yeah. What's that?
Well, with all this talk of highly calibrated ohms, microprocessor digital screens, bimetallic strips, precise multimeters, why is the ultimate recommendation for system longevity to periodically take a physical wooden dipstick and manually measure the fuel tank?
It sounds a bit backward, doesn't it?
I mean, if the engineering is so elegant, why are we reverting to Bronze Age technology?
This raises an important question about the limitations of sensors. I mean, technology, no matter how intelligently engineered or perfectly installed, still exists in a hostile physical world.
Sure.
And over time, physical realities shift. The buoyant foam on the float might absorb a tiny microscopic fraction of fuel over a decade.
Making it ride just slightly lower in the liquid?
Exactly. Or the copper wiring slightly oxidizes. The resistor tracks wear down by a millimeter. We call this calibration drift.
So the math slowly decays over the years.
Yes. And a sensor cannot diagnose its own calibration drift. It will confidently output a slightly incorrect ohm reading, and the gauge will confidently display that slightly incorrect fuel level to you.
Oh, wow.
So the manual measurement, the wooden dipstick, acts as the ultimate reality check.
It completely bypasses the electrical translation.
Exactly. It is the human element stepping back into the equation to ensure the digital representation hasn't quietly drifted away from physical reality.
So what does this all mean? We started by looking at a tiny dial on the dashboard and uncovered this brilliant, hidden chain of translation.
We really did.
You've learned how a simple float, riding the waves inside a tank, turns spatial depth into a highly specific 10 to 180 ohm electrical signal. We talked about how it utilizes ingenious thermal dampening to filter out the noise of the ocean.
And we weighed the high-tech precision of digital displays against the rugged, water-resistant simplicity of old-school analog needles.
Right. And we learned how to decode the physics of a lying gauge, understanding exactly why a severed wire causes a flat line and why a short circuit triggers a magnetic panic attack.
It's all about reading the symptoms.
Exactly. So you are now equipped with the knowledge to trace the fault, protect the translation, and ensure you are never caught off guard by an empty tank again.
It is empowering to understand the mechanics beneath the floorboards. But, consider this the next time you glance down at a dashboard. Think about how deeply we trust our lives and our safety to these invisible electrical translations.
It's pretty wild when you step back and think about it.
It is, because the gauge isn't actually showing you your fuel. It's merely showing you a mathematical interpretation of resistance. And as our vehicles, our vessels, and honestly our whole world become increasingly digital, we are layering more and more code between ourselves and the raw mechanics of the machines we operate.
Yeah, that's so true.
We have sensors translating everything, packaging the physical world into neat, consumable numbers on backlit screens. But as we distance ourselves further from the mechanical truth, we really have to ask ourselves a difficult question.
What's that?
Are we losing our intuitive connection to the physical world? Are we becoming operators who rely entirely on digital interpretations of reality rather than interacting with reality itself?
Wow. That is a profound thought to mull over the next time you turn the key in the ignition. Thank you so much for joining us on this deep dive. Stay endlessly curious, keep questioning the world around you, and we will see you on the next one.